Diesel engines are used in an increasing number of passenger cars today because they are economical and durable. A diesel engine burns diesel oil, which is also sometimes called light oil, as fuel. Unlike a gasoline engine, a diesel engine burns the fuel directly without the help of electric sparks. In this video, you will learn about the conditions that are required to cause diesel fuel to burn, how it actually burns inside the engine, and about the mechanism of irregular combustion. First, we will talk about combustion and the conditions that are necessary for something to ignite or start burning. Combustion requires three things: something burnable, sufficient oxygen in the air, and a source of heat to start the burning process. There are two ways in which something can be ignited. A substance can start burning due to a flame or spark, or it can be ignited by heat alone. Now, let's see what happens when we apply heat to some diesel oil. We will heat it carefully so that the flame does not reach the fuel directly. As you can see, the fuel begins to burn, apparently of its own accord. In a diesel engine, the fuel starts to burn like this. Where does the diesel engine get the high temperature that is needed for such ignition? When you are standing near an air compressor, you will notice that the compressor is very warm. This is because the air in the compressor warms up when it is compressed. Similarly, a diesel engine produces the high temperature needed for ignition by compressing the air in it. Now, let's see how the pressure changes in a diesel engine. The pressure is over 30 kilograms per square centimeter when the piston is near top dead center. Next, let's examine the relationship between the compression of the air and the temperature of the air. The temperature of the air increases as the pressure rises, while the ignition temperature of a mixture of air and diesel fuel decreases in proportion to increased pressure. This means that a mixture of air and diesel fuel ignites more easily when the pressure is higher. Let's put the two graphs together. Notice that the air-fuel mixture ignites more easily when this temperature gap is greater. You can see here that the air-fuel mixture will ignite easily when the pressure is about 30 kilograms per square centimeter. Now that we know this, let's see how combustion actually takes place in a diesel engine and examine the mechanism of combustion. You are now looking at a combustion chamber of a diesel engine from the bottom of the cylinder through a special piston. The piston is made of a transparent material so that you can see what goes on inside the cylinder. The film is taken at very high speed so that we can freeze the frame at some critical moments of combustion. The valves are also visible through the transparent piston. The injection nozzle is located here at the center. Let's run the previous scene more slowly so we can see more details. The fuel is injected into the cylinder from the nozzle. The fuel mist spreads out and ignites. The flames spread out in the cylinder. The fuel injection ends here, but the unburned fuel continues to burn. Combustion in a diesel engine starts and ends in a very short time. This short length of time may be divided into 4 parts, according to the nature of the phenomenon occurring in each period. The period from the injection of the fuel to its ignition is called the ignition delay period. Let's examine it in more detail. The fuel is injected as a mist from the injection nozzle into the highly pressurized hot air in the combustion chamber. This mist consists of many tiny droplets of fuel. You're looking at one of the tiny droplets of fuel in the mist. Although the fuel is injected into very hot air, it does not start to burn immediately. This is because it must first evaporate, which it does when it is heated by the hot air in the cylinder. As the evaporated fuel mixes with the air in the cylinder, it becomes as hot as the air until it is ready to ignite. The ignition delay period is this preparation period in which the fuel is exposed to highly pressurized hot air and evaporates and mixes with the air until it ignites. We saw this graph a little while ago. It shows the change in pressure that occurs in the cylinder when combustion does not occur. Now, let's see what happens when combustion does occur. Let's focus our attention on this section of the graph. During normal diesel engine operation, the fuel is injected at this point, and it ignites at this point. The ignition delay period refers to the period between these two moments. The ignition delay period must be kept as short as possible because it affects the next combustion process. The period from the time of ignition to the time the flames spread to the fuel injected during the ignition delay period is called the flame propagation period. Let's examine the flame propagation period in more detail. The air-fuel mixture is created in the ignition delay period, but the air and fuel are not mixed evenly at first. The air-fuel mixture ignites first where the air and fuel are mixed evenly. Let's run the film backward and see the moment of ignition. This is the very moment of ignition. Ignition of the air-fuel mixture creates heat, and this heat raises the temperature and pressure inside the combustion chamber even higher. This promotes evaporation of the fuel droplets and mixing of the air and the fuel. As a result, the flames that started at several diverse locations quickly spread to all other parts of the air-fuel mixture that was created during the ignition delay period. As you see here, The pressure inside the combustion chamber increases quickly as soon as combustion begins. If the ignition delay period is longer than normal, it will create undesired conditions in the engine. For example, it may allow the pressure to rise higher than necessary, or else it may prevent the pressure from rising high enough. The fuel is injected continuously from the nozzle and burns as soon as it comes into contact with the flames, which have begun spreading to all parts of the combustion chamber. The period from the time the flames spread to the time the fuel injection ends is called the direct combustion period. Let's look at the film once again. By the time the flames have spread to all parts of the combustion chamber, the temperature and pressure are extremely high, so the droplets of the fuel being injected continuously from the nozzle evaporate and burn very quickly. The pressure reaches its highest level during the direct combustion period. The ignition timing is adjusted so that the highest pressure is achieved approximately 10 degrees after top dead center. The period from the time fuel injection ends to the time combustion ends is called the post-combustion period. Let's see the film again. Combustion continues even after fuel injection stops. The unburned fuel must be burnt completely during this period. The piston goes down during the post-combustion period. This allows the air in the combustion chamber to begin expanding, so pressure and temperature drop as a result. We have just examined the 4 periods of one combustion cycle. Let's look at the film once again. Please remember that each of the 4 periods has an important influence on the following period. This shows normal combustion occurring inside a diesel engine. For the fuel to burn normally and completely, a diesel engine requires 2 things. 1, a sufficiently high pressure in the combustion chamber to cause ignition of the fuel, and 2, proper fuel injection. Proper fuel injection means proper injection timing, proper injection pressure, and the proper amount of fuel injected. What will happen if any of these important conditions is missing? Let's do a few experiments. In an actual diesel engine, the necessary heat is created by the compression of the air in the cylinder. For this experiment, we will use a gas burner to create the necessary heat. Now, we throw some wood shavings over the burner to simulate injection of fuel into the cylinder. The temperature starts to rise as the burner is brought closer to the shavings, that is, as compression takes place. The fuel is injected when the temperature of the air has reached a sufficiently high point, but the fuel does not ignite immediately because its own temperature is not very high at this stage. But once ignition occurs, the flame spreads very quickly to all parts of the fuel. The spread of the flames raises the temperature of the air to an extremely high level, and the fuel, which is still being continuously injected, starts to burn immediately. When fuel injection stops, the unburned fuel continues to burn inside the combustion chamber. A similar thing takes place in an actual diesel engine. Now we will see what happens when we change the compression conditions. You are likely to hear a sharp metallic knocking sound when the compression pressure is low. Let's see why this occurs. When the pressure is low, the temperature of the compressed air remains relatively low also. In other words, this gap is smaller than normal, and it takes a longer time for the air-fuel mixture to reach its ignition point. We can simulate this condition using a low flame on the gas burner. When the flame is low, the fuel droplets do not evaporate as quickly as when the flame is strong. In other words, a weak flame, that is low pressure, causes a longer ignition delay period. The air-fuel mixture will ignite sooner or later, but the quantity of unburned fuel in the combustion chamber is greater than normal. Once there is ignition, the large amount of fuel burns quickly, all at once. This causes the temperature and pressure inside the combustion chamber to rise much faster and higher than normal. The sharp increase in pressure causes the air to strike against the piston head and the cylinder wall with explosive force. The piston and cylinder wall then give off a sharp metallic sound known as diesel knocking. A low compression pressure sometimes also produces white smoke. Let's turn the flame down even lower than before. When the compression pressure is very low, ignition does not occur until after top dead center. Since the piston is already going down, the temperature drops and the flames do not spread during the flame propagation period. The flames soon go out and the fuel evaporates during the direct combustion and post-combustion periods. The unburned fuel is discharged at the end of these periods. That's why you will see white smoke. Now, let's see what will happen if we change the fuel injection conditions. You will also hear heavy diesel knocking when the fuel is injected too early, as we will show next. Premature injection timing means that the fuel is injected into the combustion chamber before the air temperature rises to a proper level. The fuel droplets do not evaporate as quickly as normal, and it takes a longer time before they can ignite. This results in a longer ignition delay period. Once the fuel ignites, the large amount of fuel burns at once. The result is the knocking we heard earlier. White smoke is sometimes caused also by retarded fuel injection timing. The pressure and temperature inside the combustion chamber reach the proper level by the time fuel is injected, but the retarded injection timing does not allow enough time for the fuel droplets to evaporate. Ignition, therefore, occurs only after the piston starts to go down. Since the pressure and temperature inside the combustion chamber start to drop immediately, the flames do not spread enough during the flame propagation period, and they soon go out. For this reason, some of the fuel evaporates but is discharged without being burnt. The result is the white smoke from the exhaust pipe that we saw before. Diesel knocking is caused also by low fuel injection pressure. If the fuel is injected at normal pressure, the fuel is atomized properly. But if the fuel injection pressure is low, the fuel is not atomized properly, and the size of the fuel droplets is larger than normal. Large fuel droplets cannot evaporate easily, and so it takes a longer time before the air-fuel mixture can ignite. This results in a longer ignition delay period. Once there is ignition, the large amount of fuel burns all at once and causes heavy diesel knocking. Finally, let's see why black smoke occurs when the amount of fuel injection is larger than normal. If the proper amount of fuel is injected into the combustion chamber, the fuel droplets mix with the air sufficiently and the fuel burns completely. But during excessive fuel injection, since there is only a limited amount of oxygen in the combustion chamber, the oxygen is used up completely during the direct combustion period. The remaining fuel, therefore, cannot mix with air and is roasted by the high heat. The unburned fuel turns into carbon, and it is this carbon that causes the black smoke. We have just seen 6 different experiments on the combustion conditions in a diesel engine. We've learned that combustion requires proper compression pressure and fuel injection. We've also learned that when any of these conditions is lacking, a change in the ignition delay period will occur, which in turn will affect the process of combustion and cause various types of irregular combustion. To summarize, the diesel fuel ignites by itself without electrical sparks. The diesel engine runs smoothly only if the fuel burns normally. A high compression pressure and proper fuel injection are 2 conditions that are essential to normal combustion of the fuel. It is important that you fully understand the mechanism of fuel combustion in a diesel engine and apply that understanding and knowledge in your daily work.